Here is the next question, number 48. With an armature voltage of 100 volts and rated field winding voltage, the speed of a separately excited DC motor driving a fan is 1000 rpm and its armature current is 10 amps. The armature resistance is 1 ohm. The load torque of the fan load is proportional to the square of the rotor speed. Neglecting rotational losses, the value of the armature voltage, which will reduce the rotor speed to 500 rpm, is dash. A lot of information given here. Let's begin by noting down what's given to us. So we have the armature voltage given as 100 volts and the speed of the separately excited DC motor is 1000 rpm. Armature current is 10 amps, armature resistance is 1 ohm, and this is also important here. The load torque of the fan is proportional to the square of the rotor speed. I'll note that down here. So we begin with VA1, armature voltage 100 volts. N1 is 1000 rpm. IA1 is 10 amps. RA is 1 ohm. And the load torque is directly proportional to the square of this rotor speed. So tau L is proportional to N square. So this is the relation we will have to keep in mind while solving the problem. Okay? Next, neglecting rotational losses, the value of the armature voltage, which will reduce the rotor speed to 500 rpm, is dash. So VA2 is what we will need to find when N2 becomes 500 rpm. Now, since the question talks about a separately excited DC motor, a couple of basic relationships should come to your mind, one of which is EB equals V minus IA RA. I'm sure this is familiar to you. Back EMF is equal to V minus IA RA. Now here V is the armature voltage. Now let's use this in order to find out the back EMF at the first set of values. Alright, so I'll just grab another sheet of paper here. So we are going to use the relationship that I've just written, and let's find out what is the value of EB1 when we have the values of the armature voltage, the armature current times RA. Now let's substitute. EB1 equals to, we have the value as 100 minus the current is 10 and the resistance is 1, which gives us 90 volts. So the back EMF is at the speed N1. Alright? Now for an excited motor, separately excited DC motor, we have another relation where the back EMF is directly proportional to speed. So EB is directly proportional to speed. The question doesn't say anything about the flux. So since it is a separately excited DC motor, we shall take the flux to be constant. So when the flux is constant, we have the back EMF which is proportional to the speed. Now using this, we can write down a proportional ratio. EB1 by EB2 is equal to N1 by N2, right? Now from this expression, we can find out the value of EB2. We found the value of EB1, next we find out the value of EB2. So EB2 would be equal to N2 by N1 into EB1. Let's substitute the values. What's N2? It is the reduced speed 500 divided by 1000 into 90. Solving this, we should get a value of 45 volts. So EB1 at N1 is 90 volts, EB2 at N2 is 45 volts. So we now have our back EMF values and we have our speed values. The next step is to find out the current, the armature current when the speed has reduced to 500. So that's going to be our next step. Just as we have written down the relationship between the speed and the back EMF for a separately excited DC motor, when flux is constant, we also have the current which is directly proportional to torque. Current is directly proportional to torque since phi is constant. But what has the question given us? The question has given us that the torque is directly proportional to N square. So using that, we can now write that IA is directly proportional to N square. Since torque is proportional to N square and since IA is proportional to torque, we can write it as IA is proportional to N square. We have the value of IA1. In order to find out the value of VA2, we need IA2. So this is going to give us a second relation, or a proportion in fact. So let's use this. Now this can be written as IA1 by IA2 is equal to N1 square by N2 square. Alright, I hope this is clear so far. Now all we have to do is substitute the values for IA1, N1, N2 and find the value of IA2. So we'll do that in the next step here. Okay. IA2 now equals N2 by N1 whole square into IA1. So this is our formula. Let's substitute the values. 500 divided by 1000 whole square into IA1. The value is 10. Solving this, you should get a value of 2.5 amps. Now we have the value of IA2 to be 2.5 amps. So in the beginning here, on the previous page, we have written down the formula for EB. EB equals V minus IARA, right? We are going to use that same thing to find out the value for V. EB is equal to V minus IARA. This is the basic equation. Now we need the value of VA2. This is VA. We need the value of VA2. So VA2 can now be written as EB2 plus IA2RA. Well, I hope that makes sense. All we have done is isolated VA2. So let's substitute the values. EB2 is 45. That's what we have found there. EB2 is 45 plus IA2 is 2.5. RA is 1. Solving this, we get a value of 47.5. So 47.5 volts is the final answer. 47.5. Well, this is the entire solution and I hope it has helped.